What we will be discussing today is CMP slurry monitoring, of course specifically particle monitoring in CMP slurries. So people call it chemical mechanical planarization, or also chemical mechanical polishing. So what we're going to do is we have a silicon wafer that we need to flatten to planarize. And we're going to have some kind of abrasive chuck here, and we're going to put some force on it. And what we're going to do is bring a slurry onto the surface, and the slurry is going to help us polish that surface. It'll help remove a thin layer and polish it so that it's very flat. And you can kind of think of this as a hybrid between etching and abrasives. As we had talked earlier, I used to do this mechanically at a fab back in the late 80s. We'd use acid to etch, and then we'd use weights to grind it down to make it flat, and this is a way to automate that. And what we use is a CMP slurry, which acts as the mild abrasive, which is going to help flatten that surface. This is a suspension of particles, could be silica, ceria, metal oxides of various type. And one of the important parts of the specifications of the CMP slurry is the particle size distribution, and that's what we're going to be talking about, is this size distribution. Both the mean size and something we're going to call the large particle counts, and I've seen that defined different ways by different people. Some people call it the LPC, large particle count, as the percent larger than 1 micron. I've seen people define it as greater than 0.5 micron, kind of numbers in between, so I haven't seen that exactly defined, but LPC, large particle count, is one of the focuses of today's talk. And the reason that we focus on this is because this large particle count can actually affect scratches on the surface. So if these particles end up being too large, and as there's an abrasive applied to the surface of the silicon wafer that we're trying to planarize, it can cause scratches, and these scratches then could cause a problem with yield in terms of the circuit in that particular location might be shorted and not work properly. So I'm going to show a few slides discussing this relationship between these scratches or these defects on the surface as they relate to the large particle count. In this particular publication, and I always give a reference here at the bottom when I'm showing data that we didn't generate ourselves, what we see here is on the x-axis the large particle count, and this is scratch counts. And what we see is a fairly linear relationship between the large particle count and the number of scratches. And as soon as we have a change of about 180,000 particles per mil that in this large particle count range, then it's really going to start shifting the scratches found on the surface of the wafer. And this is part of why it makes sense to do this monitoring, is because people go through all kinds of steps, filtration, etc., to reduce this large particle count, because this is a way to improve the yield, which has a big impact on the profits of the fab. I'll show data from two other studies relating the large particle count to yield. In this case, in the upper graph, we have number of particles larger than 5 microns. This is actually an older reference, as you see here. We now measure particles to smaller sizes typically, but we have large particle count on the x-axis, and here we're counting particles on the surface. Maybe it's a 10-core surface area analyzer or something like that. And we see the particle counts on the wafer very related to the particle counts in the liquid, and that kind of makes sense. So these large particles, if we reduce them, it makes sense we will reduce the particles on the surface, improve the yield. In this other study, this graph that I show down at the bottom here, here we're not looking at large particle counts, but we're looking for is they were filtering the CMP slurry with a point of use filter, and we're looking at defect density. We start with no filter, then we're filtering with 0.7 micron rated filter, and then 0.5, and we see this defect density decreasing as we do finer filtration. As we're doing finer filtration, we should be reducing the large particle count, so it is essentially the same relationship of large particle count to reduction in defect density. So we show these slides to show this relationship between large particle count and defect density, or scratches on the surface, because this is why it makes sense to invest in particle monitoring to improve the yield of the manufacturing process. A few slides talking about the instruments that we'll be looking at that were used to create the data we're showing today. The particle sizing systems has two main technologies. We have a dynamic light scattering instrument line called the Nano series. So dynamic light scattering would be good if you need to actually measure smaller than, down to 200 nanometers or so, if that's the mean size of the slurry. This would be a good way to get that mean size distribution. It can measure all the way down to 0.3 nanometers. I didn't include any zeta potential data in today's talk because it's really monitoring as opposed to just studying the CMP slurry itself, but the charge on the surface is important in these relationships as well in terms of am I using the right chemistry for the right kind of wafer. So the Nano series instrument could be used for particle size and zeta potential. But what we will really be focusing on is the AccuSizer line. And we have both an online series. We have 2 pictures of online instruments here, and the lab series. This is one of our lab instruments. And the AccuSizer is a one-at-a-time particle counter. We call it single particle optical sizing. These online units, this is a point-of-use unit. We'll see some other images of that. And this is a tower unit where we can actually multiplex multiple CMP lines into here, perform the measurement, and we have alarms and other outputs here. You can also do the measurements in the laboratory. And we have a variety of instruments in the lab that could be used for measuring CMP slurries, particle counting, and depending on the sensor, down to 150 nanometers, 0.15 microns. Sometimes we measure without dilution. If we need to dilute it, we have automatic diluters. That's what we're looking at here. The sensor actually is sitting in here, and this is an automatic dilution system. This is the counter, and depending on which sensors we use, we can kind of choose the dynamic range that we want to measure in. So let's talk a little bit about the sensors. We have different sensors, but they're all based on single particle optical sizing. In the graph you see in the upper right, we have particles coming through a constricted flow cell. We have a light source, happens to be a laser diode. And we have a detector. Now this detector could be just an extinction detector looking at the light blocked by the passage of particles, or it could look at the scattered light from the particles, or it could look at both. But the basic idea is as particles pass through the light source, it either scatters or extinguishes light. We have a detector or detectors which then look at the pulse height generated by the particle passing through there, and then by using a calibration curve convert the pulse height distribution into the particle size distribution. If we didn't need to measure the smallest particles, we have a sensor which is a combination of extinction and scattering, the LA400. You see the dynamic range here, 0.5 to 400 microns. And when we talk about the concentration limit, this has to do with the coincidence limit. We don't want more than one particle at a time passing through the sensing zone, and so we talk about at what concentration limit can we operate with confidence that we were looking at single particles and not events where there were multiple particles in the scattering zone. So one way we can increase the concentration limit is by making the zone where we take the measurement smaller. If we focus the light source, we have 2 ways to approach the FX and the FX Nano. You see these specs here, we can get down to 0.65 microns or 0.15 microns depending on the requirement for the slurry. And these work at up to about 200 times a higher concentration rate than the standard sensor. So depending on the sensor we put into the fluidics, we have multiple fluidics. This is one of the point-of-view systems. We can put different sensors in here, and they'll work at different size ranges and different concentration ranges. If we want to work with no dilutions, we might use the FX or the FX Nano sensor. This will help us with statistical accuracy, and these still have this excellent sensitivity to the large particle count, and we'll look soon at some data comparing optical particle sizing to other techniques. This is data, for instance, from a Ceria slurry that was measured at full concentration. And that's what people like to do. And when we measure a new sample, what we often do, for instance, is a concentration study. When we look at a slurry we don't know, and we measure it, and then we dilute it, and we see if we get a proportional decrease in counts. And that tells us if we're working at a concentration range where we don't have to be concerned about the coincidence limit. We're going to talk today about some various applications of why people do these measurements and how people have used it to do a lot of good things. What we'll see here is that we can measure these tails at high concentration. We can do it without dilution, or we can do dilution. We can sometimes work with customers. For instance, this is a delivery system from a company called EMI, which is a partner of ours up in the Northwest. And sometimes people need us to integrate our sensor into the delivery system. Sometimes we're just at point of use. But basically we can work with customers so that we choose the fluidics that works best with the process. And what we're going to do is monitor things like filtration, pumping, the mixing, or what happens with the aging of the CMP slurry. This is just a little image of us catching a few large particles here. This is looking at particle size as a function of time. And this is the kind of things we do. We have to figure out where's the best place to integrate the measurement into the system, which is the best fluidics, dilution, no dilution, and what is the best sensor. And what we'll start doing now is looking at some data generated looking at some CMP slurries. Now, optical particle sizing has proven to be the most sensitive technique for finding these tails, these few large particles. And this is an older study made by some people. I give the reference down here. What they were doing, it was a silica oxide CMP slurry, and then they were spiking the CMP slurry with 1 micron silicon dioxide particles. And what you see on this graph is, this is on the x-axis, the amount added of the spike material, and this is the relative signal. So what they do is they'd measure the sample, and then they'd measure the sample plus the spike and look at the difference. And what you see, this graph on the farthest left is the AccuSizer. This was an online AccuSizer. And they compared it to these other vendors, and I'm always polite, and so I'm only showing the AccuSizer data, and I removed the names of the other vendors. But one thing I'm going to say here is the data from the AccuSizer, and this one you see over here is squares, is actually a laser diffraction analyzer, and one I'm fairly familiar with. And if you look at, for instance, at this particular concentration range, if you look at the difference between the AccuSizer and the laser diffraction analyzer, if this is around 1 and that's at around 100, so we're at least 100 times more sensitive single particle optical sizing than you are using laser diffraction for finding these outliers, these tails. So I guess maybe sometimes people would use something like laser diffraction to look for the mean particle size, and it's capable of looking at smaller particles. But if you want to find these few large particles, we're at least 100 times more accurate or more sensitive to find these large particles than laser diffraction. And compared to some other techniques we see, 1,000 times more accurate. In this particular publication, the AccuSizer could actually pick up as soon as there was 0.07 mg per mil of the spiked material, we could find it. So we carried out our own study recently. I was up in Santa Barbara. Dave Nicoli, our founder, was running these samples while I was visiting. And what we were doing is we were taking different silica slurries and also some other slurries. We're just going to call them a slurry A, B, C because we don't talk about our customers' products too often in public. But we took these standard slurries. In this case, with this slurry, we were diluting it 200 to 1. And in the next two slides, the spike particles we used were just 1 micron PSLs. So these are the Duke Scientific thermoparticles, whatever we call them now. So we're taking 1 micron polystyrene latex standards, and we're spiking the CMP slurry. We actually were adding a known concentration, as you see here, and we did the calculation saying, you know, with this spike of adding this amount into the slurry, we'd expected to see an increase of about 100,000 particles per ml here at 1 micron. And here you see in the graph the spike clearly visible. And as you look at the tables here, this is 300 and something thousand, this is 200 something thousand. So it picked it up right at the concentration we expected as well, at 100,000 particles per mil. Here are two other slurries that we investigated. Slurry B we measured without dilution. What you always see here first is this blue line is the sample without the spike, and you see a few large particles but a fairly stable baseline. And as we added the spike, this was at 5,000 particles per ml. Easily picked up that spike. And then in slurry C, where if you look at the original data, which is the blue line, it wasn't quite as stable here. You know, there were already a few large particles in the slurry, but we actually spiked it pretty gently with only 2,500 particles per mil of the 1 micron PSL particles, and we very clearly picked up on the spike. So this is us just proving that this is the technique for high sensitivity for picking up this large particle count, and that's why we're so popular in this industry for measuring these CMP slurries. Now let's look at some of the ways you would use this tool. We do filtration to reduce this large particle count so that these particles don't appear on the surface of the wafer. And there are various places where we could do the filtration and do the monitoring. So maybe in bulk the CMP comes in something in a tote. It goes through a mixer, maybe there's DI water added because you're diluting it, or maybe some other chemicals. That's pushed over to a day tank, and then from here you're probably starting filtering, and then as it goes through a manifold out to the polishing tools, you probably have point of use filters here as well. Now you could measure here just as you go through the recirculation system, or you could measure right at point of use before you get onto the wafer, either place. Of course, in our mind, you should put one of these analyzers everywhere you have a filter, but you could put this here in the circulation loop or here at point of use. What we see here is actually in the supply line. This is a study where people measured up here in the supply line. And what this was looking at is what happens to the particles greater than a micron as a function of time. And what this helps us see is when is it time to change the filter. So here you see the particle count increasing, and you don't want to have the counts pick up that high, so it's time to change the filter. So what this will help you do is know when to change your filters, not just based on looking at a watch and saying, yeah, we do it every 2 days or so, but base it on the particle count, because that's really giving you that feedback of when is it required in terms of what's going to interact with the silicon wafer. This will both help you reduce that count on the wafer, which should increase your yields, but it also lowers costs because then you're only changing the filter when you need to, and the filters aren't free. So one very good use of using a point-of-use particle size analyzer in these systems is to know when to make the filter changes. Now we could also just recirculate that sample, and as it goes through the filter we could see how good are we doing in terms of filtration. And this is a study I found where somebody was comparing filters. So you're trying to figure out who makes the best filter for me to put into my system. And these are two competitive filters. I removed their names. What this was doing is looking at, this is before we start recirculating through the filter, and then after 10, 60, 2 hours, and 180 minutes, how does the particle count reduce as a function of time as it's filtered? And here we're seeing a greater reduction in particle count, so maybe this is saying this is a more efficient filter. And another good way to use these instruments is to choose what are the best filters to use in your process. Here is another study I found where this is just a picture of, they're taking the main slurry system, recirculating through the day tank through a main filter to a point-of-use filter. And this is a little closer look. We have the point-of-use filter as the slurry then comes down and interacts with the pad. And in this study, it was just trying to say, well, do we really need to have filtration? If you look at the particle count here, size versus particle counts, when there's no filter, the green line is fairly high. But as we put in this point-of-use filter, look what happens, a great reduction in the particle count. We see the particle count going from 5,000 to 17,000 down to a couple thousand or just 500. Using this point-of-use filter really reduces the large particle count. So maybe this helps justify this expense of getting these filters into place. Here's data where we're just going to recirculate the sample through the system. This is the particle count as a function of time without a filter. Now, one of the ways that you could cause agglomeration, we believe, is just by adding shear force to the CMP slurry. And as you're recirculating this, it doesn't matter which pump you're using, the CMP slurry is going to experience some shear forces, and that can cause some agglomeration. So we start seeing the large particle count increasing. But then as we stick a filter in the recirculation line here, this is a 10 micron, a 5 micron, and a 1 micron filter, then we see the LPC count drop down dramatically. So this could help you choose, well, what rating of a filter do I really need in here? And you can choose, do I really, because as you get to smaller size rating filters, they're more expensive. And so you can use a tool like this to decide what rating filter should I be using in our system. So as we pump the sample, this is another study I found where the data is all from the AccuSizer, and they took a fresh sample, and what they did is they had two-stage filtration. They looked at what goes on as it goes through a 5 and a 3 micron filter, and this is the first feed, and then as they start recirculating it, you can see the particle counts increasing with time. Now as we're filtering it, that is reducing the large particle count, but how many times can you recirculate it before you really start having to be concerned? So here you see the increase so this is the first feed, and then as it's recirculated 2, 3, 4 times. And what we're seeing is, sure, we can reduce this large particle count, but if you just have a 5 micron filter, you're probably going to get into trouble. So again, another study where the AccuSizer is used, saying what's the effect of filtration, what's the effect of pumping, what kind of filters should I be using in my system? And that's a very common application. But now we're going to look at some results just where we're looking at the effect of pumping. And what we see in the upper graph, these are pumping using two different pumps. So this is two things. What's the effect of pumping and which kind of pump do we use? This particular pump or a standard diaphragm pump. Now here this is medium particle size, and this actually, the upper graph is data taken from a laser diffraction analyzer. And you really don't see too much change. The median particle size stays about the same. But then in the same study, they were also doing measurements with the AccuSizer, looking at the large particle count as they defined as larger than about a half a micron. And the AccuSizer actually caught the large particle count increase on the diaphragm pump, which wouldn't have been caught using the laser diffraction analyzer. So this is a point, again, diffraction, good way to find the mean size. The AccuSizer, the best way to find this large particle count. And in this case, it was very sensitive and could help people pick out which is the best pump for this particular process to reduce the large particle count. This is some data a customer shared with us. These series, this is runs, and this is different sizes, like this is probably the large particle count here. And yes, as we pump through the system, we see that the large particle count increases as a function of time. And this could easily just be to the shear force from the pumping. Two other slides that we received from customers. This is different sizes here. So this is the largest size, and what we see as we keep recirculating the system, we see all particle sizes increasing with time and the large particle count changing with time. This study down here, this is looking at online slurry monitoring, and then here's an upset. And this is when scratches started appearing on the surface of the wafers. So what you see here is, again, the benefit of this continuous point of use monitoring. You don't get this data if you just take samples and bring it to the lab. This is the benefit of the point of use or the online sensors, so that you are continuously monitoring the slurry and knowing there are upsets, which probably, and in this case did, create scratch issues on the surface of the wafers. A few more studies. This is looking at the top and bottom of a tank, and I've actually heard that in some of these fabs they only use a CMP slurry from the top, maybe 2/3 of the tank, and the bottom they don't use. Now here is we take a slurry, and what you see along here is we're looking at the particle count from the top of the tank. And then as we switch over towards the bottom, look at the jump in the particle counts across all these size ranges. So sure enough, particles, even when they're colloidal particles and they stay in suspension, there's probably some settling and other effects going on. And this is kind of an indicator of, if you want to be super careful, maybe you're only using this slurry near the top of the tank, not right from the bottom. And this graph down the bottom is just LPC as a function of time from a day tank, and just looking at what's happening as a function of time, so you know how to optimize that process. Another way where we might want to use particle counting of the AccuSizer is to look at what's the effect of aging of the slurry. A new slurry is probably has better health than a very old one, kind of like the rest of us. In this particular study, this was a mixed abrasive slurry. It started out as a silica slurry, and what you see here is particle size, and this is the raw data, and then they just measured it over a function of a month. They took measurements in the lab, and they saw some increase in the silica slurry as a function of time, and it was getting worse with time. I think we see the mean size going from something like 1.3 up to 1.72. Now here in the bottom side, what they did is then they mixed in the alumina and made this a mixed abrasive slurry, and the alumina was either annealed or not annealed. And what you see on the left-hand side, this is the annealed mixed abrasive slurry, and it didn't change that much over a course of a month, a little bit, but if you look at the non-annealed alumina, a big change over a function of time over the course of the month. It went from a mean size here that's around 3 to a mean size after a month that's up here at around 6.5. So a good way to look at the effect of aging on the slurry, and in general, younger is better. And this is a study we did ourselves. This is taken from an LE400 sensor, so not our most sensitive, but it could pick up the fact that as we took this cerium oxide slurry and exposed it to temperature, here's the highest temperature exposure, sure enough it started causing difficulty with agglomeration or some kind of aggregation, and it's a way to speed up the aging of a slurry is to heat stress it, and sure enough, don't heat stress your slurry. So that's the data I wanted to show today, and we looked at the effects of all kinds of things. Should I filter? Which filter should I use? What rating filter? How often do I change it? We looked at the effect of pumping. We looked at the effect of aging, and for all of these effects, if you need to know what's going on with the large particle count, the AccuSizer is the instrument we think you should be using. You can do lab measurements, or if you're really concerned about yield, these point-of-use sensors, that's probably the most effective way to increase your yields. We're very happy to work with our customers in terms of making sure that we have the right sensor, the right fluidics, the right dilution if we need it. We work with customers to make sure we deliver the system that's best for your process and needs, to make sure that it is a worthy investment to increase yields, because you know what, that helps you buy more of our instruments. That's the presentation I wanted to give today, and the last point I'm going to make, other than thank you so much for coming, is just make sure you do visit our website to get updates on new application notes. For instance, the data I showed you where we spiked the 1 micron PSL particles is an application note that I put together recently that if you go to the website you can request that to download to get more details. So please visit pssnicomp.com, and from here you can request the latest information to make sure you know what technology we have now and exactly how we can help you best.